Assalamu alaikum, welcome back. So we are now in lecture 8, introducing the Standard Model Part 2. And we had left off talking about the structure of the atom, that it's made up of a nucleus and outer electrons orbiting the nucleus, and that the nucleus is made up of protons and neutrons, with the protons being positively charged and the neutrons being neutral in electric charge, and the electrons, of course, are negatively charged. For the longest time, scientists thought that these three fundamental particles, the electron, the proton, and the neutron, were the most basic constituents of matter. But further work developed something known as the Standard Model, and it turns out that protons and neutrons were made of yet smaller things. And those smaller things, I'm sure you've heard of, are known as the quarks or quarks, depending on how you want to pronounce it. I like to say quarks, but it turns out that here is the atom, here is the nucleus, and protons and neutrons are made up of still smaller particles that are the quarks, and a proton is made up of two so-called up quarks and one down quark. Now, we said that the proton is positively charged. It has a charge of +1. And it turns out that the up quarks carry a charge of +2/3, the down quark a charge of -1/3. So if we look at the proton having two up quarks and one down quark, that is 2/3 plus 2/3 is 4/3 plus -1/3 gives us a total positive charge of 1. The neutron is made up of a slightly different combination, two down quarks and one up quark. And when you add up these charges, -1/3 plus -1/3, that's -2/3, plus the +2/3 of the up quark gives us a total charge of 0. And that is why the proton has a charge of +1 and the neutron has a charge of 0. The electron cannot be further subdivided, at least up to our current knowledge. So now scientists believe that all matter is made up of only three particles, but instead of electrons, protons, and neutrons, they are the up quark, the down quark, which together make up both protons and neutrons, and the electron. These are the most fundamental constituents of matter, and scientists believe they cannot be further subdivided. So it seems sort of simple then. However, it turns out that as particle physicists were investigating particles in high energy colliders, they found an awful lot of different particles. And things were more complex than this picture. And further work on their part gave us what is known as the Standard Model of particle physics. And this is sort of a busy slide, so let me go through it with you. That all matter, as we said, everything that we know is made up of up quarks, down quarks, and electrons. And it turns out that matter is divided into two families, quarks and so-called leptons. And the quarks are the up quark, the down quark. The leptons are electrons and neutrinos, very tiny neutral particles. They carry no charge. And in fact, as you've been listening to me, billions of neutrinos have passed through your body. They stream right through ordinary matter because they are extremely light and carry no charge. And so we added the neutrino. Again, the story of its discovery is quite fascinating, but takes us far afield. And everything we know then is made up of up quarks, down quarks, and electrons. And we also know that there are neutrinos, but they don't enter into the makeup of ordinary matter. They are given off as one thing changes into another, for example, radioactive decay, and actually neutrons changing into protons and so forth, and we'll talk about that more later. But it turns out that even though there are 4 fundamental particles, nature was a bit stranger. There are actually 3 families of very similar 4 fundamental particles. So not only are there the up quarks and down quarks that make up the protons and neutrons in ordinary matter, but there's a second generation of quarks known as charm quarks and strange quarks that, except for the mass, they are heavier than up quarks and down quarks, behave precisely like up quarks for the charm quark and down quarks for the strange quark. And the electron has a heavier cousin that also carries a charge of -1, just like the electron, but is heavier, known as the muon. And there is a neutrino. You notice here it has an E. Well, that's known as an electron neutrino because it's part of the first generation of the Standard Model. Not to be outdone, there's also a muon neutrino. So it turns out there's a second generation of quarks and leptons that are made up of the charm quark, strange quark, the muon, and the muon neutrino. Also, it turns out there is yet a third generation of quarks, and they are known as the top quark and the bottom quark, which are just like the up and down and the charm and strange, but heavier still. And a third generation of leptons, just like the electron, just like the muon, known as the tau, but heavier than these two. And the tau has its own version of the neutrino known as the tau neutrino. So basically, the universe then is made up of 3 families, each family having 4 members, 2 of them quarks, 2 of them leptons. But all of these enter into particles that very quickly decay into our ordinary matter. And our ordinary matter is made up of just up quarks, down quarks, and electrons. And the neutrinos play very important parts in particle transmutation and decays. So 2 very important issues pop up that we will talk about very shortly. But these then are the particles, 12 particles that are made up or that are constituted by 3 different families: first generation, second generation, third generation, each generation having 4 particles, as we said. There are sound theoretical reasons in the Standard Model why there should be 4 particles per generation. But as of now, nobody has any idea why nature decided to have 3 generations instead of just 1, which makes up all of our ordinary matter and our universe. So no one has a clue why there are 3 generations, but scientists feel very strongly that no 4th generation will be discovered. And I have to mention that each of these particles also has its own antiparticle. So this is what makes up ordinary matter, but you've probably heard of antimatter. We've certainly heard of it on Star Trek. And so instead of 12 particles, there are really 24 particles. All of these particles plus all of their antiparticles. So the antiparticle of the electron is exactly the same as the electron, except its charge is +1 instead of -1. That's known as a positron. And all of the other antiparticles just get the name anti in front of them. Like the muon has an antiparticle that has the same mass, but a charge of +1, and it's called the anti-muon, and so on. Neutrino has an anti-neutrino, etc. So these then are the particles of the Standard Model. These particles are interacted upon by forces, and it turns out that the forces are mediated also by particles. So forces are mediated by the exchange of so-called force carriers or force particles, and those particles are the gluon, and the gluon mediates something known as the strong nuclear force, the photon, which mediates the electromagnetic force, and the W bosons, and they come in a +1 and a -1 charge, and the Z bosons, and they mediate the weak nuclear force. So nature then has these 12 particles plus their antiparticles, and it has a strong nuclear force mediated by gluons. And the strong nuclear force, we will talk about in due time, it is what glues together the up and down quarks to have them make protons and neutrons, and what glues protons and neutrons together in the nucleus of an atom. The electromagnetic force is mediated by the photon, and the photon is also the carrier of light. And the electromagnetic force is what causes the interaction between positive charges and negative charges. So if we go back here, the strong nuclear force is holding these up quarks and down quark together to make a proton, and holding the protons and neutrons together that make a nucleus, because, as you remember, positive charges repel. So a bunch of protons stuck together in a nucleus would want to fly apart because their positive charges repel. Why doesn't the nucleus fly apart? It doesn't fly apart because the up and down quarks inside it keep exchanging gluons that produce a strong force that not only keeps the proton together as a proton, even though it's made up of two up quarks that are positively charged, plus a down quark, but also keeps the protons and neutrons together in the nucleus. So that's the strong force. The electromagnetic force is what is going to be responsible for the attraction between the positively charged protons and the electrons that are spinning around the nucleus. And the weak nuclear force will be in charge of a lot of different transmutations of particles and things like radioactive decay. And we will talk, inshallah, about that when the time comes. And we need to mention the Higgs particle, the famous Higgs particle, which was discovered only recently, even though it was theorized a long time ago. And the Higgs particle is what gives all of these particles their mass. It is responsible for creating a Higgs field that kind of causes resistance as the particles try to move through it. And that resistance is what we interpret as mass. So there are 12 particles plus their antiparticles, the strong nuclear force mediated by gluons, the electromagnetic force mediated by photons, the weak nuclear force mediated by W bosons and Z bosons, and there is also the gravitational force. So there are 4 forces in the universe: strong nuclear force, electromagnetic force, weak nuclear force, and the gravitational force, which does not yet enter the Standard Model. People feel it is mediated by gravitons, but they have not yet been discovered. So this then is the Standard Model of particle physics. And when we come to talk about fine-tuning, we will then be talking about the constituents of this Standard Model and why they need to be exactly what they are. So let's just flesh that out a little bit then to end this introduction. So when we talk about up quarks, down quarks, electrons, and so forth, they have properties. One of the properties they have is electric charge, which we've already talked about, positive 2/3 for the up quark and for the charm quark and top quark, negative 1/3 for the down quark, strange quark, and bottom quark. For the electron, the charge is -1. For the neutrino, it's 0, for example. They also have mass. And so if we take a look at the mass of the electron, it is extremely light. It actually weighs 9.1 times 10 to the -31 kilograms. So we would take this 9.1 and move this decimal point to the left 31 places to get the weight of an electron in kilograms. But remember, by Einstein's famous E equals mc squared, that mass and energy are interchangeable, we can actually express this mass in more convenient units that are units of energy. And if you were to take this mass in kilograms, multiply it by the speed of light squared in appropriate units, you could then convert this mass into energy because they're the same currency. And the mass of the electron that you see here is 0.511 mega electron volts. That means million electron volts. Each electron volt is the energy that is needed to move one electron across a potential of 1 volt, or the energy really that the electron acquires, to put it more correctly, as it moves across an electrical potential difference of 1 volt. That is known as 1 electron volt. It's a very small amount of energy. If we take a little over 500,000 of those energy units, that is the mass of the electron. So the electron is 0.511 mega electron volts, MeV for short. So each of these particles then can be expressed in the same units. The weight of the up quark is 2.3 MeV, 2.3 mega electron volts. Here's the weight of the down quark, and so forth. And for example, the up quarks are about 4.5. The up and down quarks, forgive me, are 4.5 and 9.4 times heavier than the electron. If you were to take the 2.3 and divide it by 0.511, you would get this roughly 4.5 and so forth. The other 4 quarks are much heavier. They are 190 times heavier, 2,495 times heavier, 8,180 times heavier, and 338,960 times heavier. And in the lepton family, the electron's cousin, which is identical to it, the muon, in everything except mass, the muon is 207 times, forgive me, heavier than the electron. And the tau particle is 3,477 times heavier than the electron. The neutrinos are extraordinarily light particles. For a long time, they were thought to have 0 mass, but now we know that they do have mass, but an extremely small mass. And what you see here is the electron is about 500,000 electron volts. The neutrino weighs less than 2.2 electron volts. Nobody knows its exact mass. So the interesting thing, and the thing that we will talk about, is no one has any idea why these particles have the masses that they do. No one knows why the electron's mass is 0.511 MeV, and why the mass of the muon is 105.7 MeV, and so forth. There is no physical theory that can predict this. We simply measure these. These are givens. And why do they have this amount of charge? We have no idea, etc. Same goes for the force particles. The force particles produce a certain force. We said the gluons produce an attractive force between the quarks. That force has a certain strength that is given by what is known as the strong coupling constant that measures the strength of the strong force. The electromagnetic force also has a given strength. So 2 negative charges repel each other by a given force, or a positive and negative charge attract each other with a certain amount of force mediated by the electromagnetic force coupling constant. And that is expressed in something known as the fine structure constant. Same thing with the weak nuclear force. And it also turns out we have no idea why these forces have the strength that they have. But surprisingly, it turns out that part of the fine-tuning of the universe is that if we mess around with these fundamental properties, like the mass of the up quark and the down quark, or the electron, or the amount of the strong nuclear force, or electromagnetic force, or weak nuclear force, if we try to fiddle with those, the universe cannot sustain anything resembling life. There would be no matter, no complex chemistry, none of the things that we associate with life. And this came as a total, I don't even want to say surprise, it came as a total shock. People initially thought there'd be fairly wide latitude. We don't know what the mass of why the mass of the electron is what it is, but it doesn't much matter. If it was a bit lighter, a bit heavier, matter would be a little lighter, a little heavier, who cares? If gravity were a little stronger, a little weaker, we've already seen how disastrous that would be. People thought things would be just a little bit heavier. But in our first lecture series, we've already seen that you can't fiddle with the force of gravity. It turns out the same goes for the other forces. And all of these fundamental properties of the basic constituents of nature, the basic constituents of the Standard Model, are very, very finely tuned to the existence of life. And if we try to fiddle with the constituents of the Standard Model to make them have slightly different properties, no matter, no chemistry, no life. And that is a very, very amazing thing. And it will be, inshallah, part of what we will explore in our next lectures coming up. So I hope I have interested you in that, and I hope you will tune in, inshallah, for those. Take care, and salam alaikum.